because I find it difficult to upload actually. Okay, now I want to test the voltage. Okay, just to show you there's no trick, I want to measure the voltage here again for the input. So it's 0 because this meter has to change it to AC. I had this issue last time. It took me some time to figure out. 2.8 or 2.9, so more or less the same. Basically that's 3. And last time I get shocked because I did not switch it off. I just put my finger to this and I get shocked. So this time I learned my lesson. I'll switch it off first. And I'll put this to, I want to measure the voltage over here. And I'll switch it on again. 3V. And you see the display is weird because it exceeded the limit. As I said, 20. Just like the voltmeter you use. So I have to set 200. And you see the voltage now is about how much? 55 roughly. Why is it not 60? Am I lying?
Yes.
I'm not lying. But there is a reason why. Resistance where? In the wire. And also, apart from the wire, which is true, the transformer itself has efficiency issue as well. It's not 100% efficient. None of the transformer in the world is 100% efficient. Why? Again, apart from the resistance, you can see, other than that, there's also one reason. Think about how actually this transformer works. Think about this. If the current going through this coil, inside it, you know there are coils inside. And what will happen to this coil? Heat, and yeah, that take up some energy. But mainly, in terms of working principle, what would they do if you have current? You have B field, very good. And what happened to that B field? In this situation, the B field will be passed along the soft iron core, right? Just like the iron nail you use in the electromagnet. And that means this B field will go into this coil, in this hole basically, going through this. And it's changing because it's AC. So you go up and down on this part, and also up and down here all the time. In this case, if you are changing the B field all the time, what will happen to this coil? Heat up, and also mainly, according to Faraday's law or Lenz's law, not move, but you have the induced currents in this coil, right? So that's why you have the currents induced here and also passing on to the other side. Remember that these two are two separate circuits actually. You just put them close together so that the B field can pass on. And that's also how the wireless charging, if you ever used one before, work. You use the B field to transmit the energy as well. Anyway, the B field will also leak here. Can you imagine that? The B field, it go in all directions, right? Of course, most of them go through the soft iron core, but some of them are gone to the atmosphere. So that's why it's not 60, it's 50 something. If I now try to put away this soft iron core, just this one, even this one, it's not completed, right? Try to see what happened. The light is not on as well. And the voltage here is only 10V. That means output here. You try to step it to 60, but eventually you only got 10. That means those 50 has been gone to the atmosphere. Yeah? Gradually this will get hot as well. So I'm not going to do this for long.
Mr. Wong, can you explain again how the transformer works?
Okay.
The B field. Yeah.
The B field got induced here. So if you use the hand rule, basically it's either this side or this side. But since it's AC, so it keeps changing, right? In this case, the B field will be transmitted along here.
Yeah.
Sometimes go down, sometimes go up.
Yeah.
Actually, all continuously changing. So in this case, if you keep changing the B field, according to Lenz's law, okay, why step up? Right? The next question, why step up? Think about this. You have more coils here, so you experience more B field change. If you remember how you build the motor or how to build the electromagnets, the more coils, meaning that you can have more B field generated or received. So in this case, if you have more coils here, then the voltage will also be higher. Makes sense, right? Coils will be more coils, more voltage over here. That's how it step up. On the other side, step down is just opposite. Now what I want to do is I want to measure the voltage here, just to check. It's about 2.1, 2.3 maybe. So that's why this light bulb is much brighter than the DC that one, than the Edison that one. Is that okay for you so far? Now I want to do the next thing is, as we said, it only works with AC and it shouldn't work with DC. Why it shouldn't work with DC actually? Let me show you first. Without changing anything, I just plug this into the DC. Okay, and let's have a look. 3, 2, 1. On. Not even anything. And it's not working. Why? Tell me why.
If it doesn't keep changing.
Good point. If this is DC, let's say I don't even know what to check this one. Let's say the B field is like this here, and then when it's passed on, it go down, but it's always going down or always go up. Doesn't really matter here. Let's say always go down. Then what's the problem here?
There's no magnetic.
There is magnetic flux or magnetic field, but the thing is the magnetic field is not changing. So how come this will be an issue?
You have to change in order to induce it.
Very good. Lenz's law. Lenz's law said you have to change the B field. There's two ways you change it. You either cut it, or the B field itself is changing. So if the B field is not changing, then no current, no voltage will induce here at all. So in this case, this would even be 0V in this case. And that's why the voltage cannot be passed on there. And that's why we must use AC. And I think that's it. Yeah, so that's why you must use AC. And that's also why your sockets at home, you have to use AC. So that helps you to change your voltage easily. Because let's say your phone is not working at 220 V. It's working at, do you know how many? How many V? Let's say iPhone is about 5 V. So if you charge your phone with 220 directly without transformer, obviously it will explode, it will get overheated. So that's why you need a transformer. If you go home and try to try to break the charger inside, it's basically coils, nothing more, just coils.
Transformer.
Yeah.
So if you put like wireless charging phone around here, it will charge.
Yeah. Yeah. Any questions? Okay, if no, you can go back to your seat.
Did it stop?